Okay, hi everyone. So I know this second and I guess third part of the review is coming late. This is actually, I've tried to record it so many times and been working for a few hours to try to upload it. And every time it's been crashing. So this is gonna be my final attempt. I hope that this works and I hope I can get this out to you guys. But anyway, just wanted to explain why this has been taking so long. So this is the second part of the content, and so the focus of this will be on the nature of waves and then specifically features of sound specifically. So first of all, what is a wave? So to explain this, we're going to go back to where we left off last time, where we have all these air molecules, which usually air molecules don't look this orderly, but we know that they're moving really randomly, really quickly due to what? Due to Brownian motion, right? And so these air molecules are moving all over the place. And then imagine that there's this disturbance that comes in, and basically, as this disturbance moves through, it's causing this transfer in energy. So there's this disturbance of some sort that causes a transfer in energy. And basically, what this does is it causes a change in pressure of the molecule. So, for example, if the wave is moving this direction, these molecules may become really high pressure, right? And then these molecules would be low pressure. So, this would be like a low versus high pressure area, right? And so, there are these changes of pressure in pressure within that medium. And that is essentially what a wave is. So the main thing to note though is that a wave is not, I guess maybe more than asking what is a wave, what is not a wave? A wave is not matter. Oh, let me say not matter, so we don't get that confused. It's not matter. And so what that tells us is that there is no mass, there's no volume, there's no other feature that we would associate with matter, although the wave is moving through matter. So it's moving through a medium. It could be a gas, a solid, a liquid, any state of matter. But the wave is more like a form of energy, or it's causing this transfer in energy. And there are two types of waves that you need to know. There is a transverse, let me use a different color. There's a transverse wave, and there's a longitudinal wave. Longitudinal wave. And this is a really important difference to note. So when we have a transverse wave, so let's say both of these waves are moving in the same direction, right? Because waves, they propagate, they move. And so they're moving through some type of medium. And once again, we have these little particles going like this. And so basically, what happens with a transverse wave is that the particle, or sorry, the particles in the medium will vibrate perpendicular to the direction of the wave. So if the wave is traveling this way, right, it means the particles are moving this way. They're moving up and down. So in this case, if some of these particles are moving up, some of them are moving down, and this is where we see our nice little waveform start to originate. So it looks kind of like that. And the peaks of this, of a transverse wave specifically, the peak will be called the crest, and that bottom lowest part will be called the trough. Okay, so the main thing to note is that this is a perpendicular movement. Perpendicular movement of the particles. And what happens with a longitudinal wave, however, is let's say we have our particles again. So instead of moving perpendicular to the way that the wave is traveling, so the wave is traveling this way, right? Traveling this way. But instead of moving perpendicular the way a transverse wave does, it actually will move longitudinally. So it's parallel. So instead of being perpendicular, the particles are moving parallel to the direction of the wave. Parallel movement of particles. And so basically, the best way to kind of visualize this is imagine that a longitudinal wave is kind of like a spring, where you have these places where the spring is really spaced out, and then you have other places where it's really close together, and then it may be in between at some point. So you'll kind of alternate through these regions. And basically, let me move this part down a little bit. Oh, I need to do that. So basically what happens is we don't have crests and troughs for this, but we have these areas called compression, and then these areas where it's really spaced out is called rarefaction. So these areas of compression, what are they in actuality, is that they're regions of high pressure. So basically, because of the movement of that wave, the particles are going to be really close together. But with the areas of rarefaction, the particles are really spaced out, so it's going to be an area of low pressure. And another important thing to note is that longitudinal waves can be drawn the same way that transverse waves are drawn here. This is a waveform, by the way, which is also important for you to know. This drawing is a waveform where this line right here, the x-axis, represents time, and on the y-axis we have amplitude. And so both transverse and longitudinal waves can be represented with a waveform, but the main difference is that if we're talking about longitudinal waves, when it's drawn in this waveform, like so it looks the same, but these peaks will be called compression. So this is when pressure is higher. So that's compression, and then these the lowest portions will be called rarefaction, which is the area of low pressure. And yeah, just remember that with transverse waves, it's moving perpendicular to the way that the wave is traveling, whereas with longitudinal waves, the particles are moving parallel to the way that the wave is traveling. But they can both be drawn by using waveforms. So next I'm going to move on to what is sound. And also I'm just going over the most either challenging concepts or concepts that I just found were more important. So please note that there are other concepts in this unit, but I'm just kind of skipping around just because of the time constraint. So we define a wave, and we know that there are two types of waves, right? Transverse and longitudinal. So then what is sound? And this goes to the whole general idea that we have of defining this nature of sound. So one thing we know that sound is a wave, right? And because it's a wave, what does that mean? It means that it's not matter. So remember, its sound will not have a mass, it will not have density or volume or any of the things that you would associate. So I'm gonna just say no mass, and then you can fill it in with density, volume, etc. Like it doesn't have any qualities of matter. Actually, it's more like energy. And specifically, sound functions as a longitudinal wave. So that's also important to know. It's longitudinal. And why do we know that? Because sound causes a change in pressure. So it causes a change in pressure within whatever medium it's traveling in. So when we hear sound, it's mostly traveling through air, so through a gaseous medium. But it could travel, sound can also travel through water, it can travel through solids. So all in all, though, sound is a longitudinal wave because it's causing this change in pressure, which means that it causes both compression and rarefaction. So remember, compression is high pressure regions, rarefaction is low pressure regions. And basically what happens is um, let's say when we hear a sound, another good way to describe this would be saying that it's a vibration, right? So it's kind of a vibration of the molecules, whether it's air molecules or whatever. So if we go back to drawing our molecules here, we have all these molecules, and then there's the sound wave coming through, and I'm just going to draw it with our little waveforms. The sound wave coming through, and it's causing all these so it's kind of this vibrating thing that's causing these particles to move around and have all these high pressure, low pressure qualities, and so it's causing this change in pressure, right? So let's put that change in pressure here. And basically the sound wave is going to propagate all the way to your ear. And I'm really bad at drawing the ear, but just imagine that this is the ear. Um, I'll label it as the ear. And we're going to go more in depth about the auditory system and the anatomy of the auditory system. But here we have the eardrum or the tympanic membrane. And basically, when the sound reaches the ear and it goes into the ear canal, it actually causes the tympanic membrane to vibrate. So the tympanic membrane or the eardrum will vibrate. And these signals essentially, and again, we'll talk more in detail about this, but these signals go to the brain. So the signals go to the brain, and the brain interprets it or perceives it as sound. So perceived as sound. So that whole question, like if a tree falls in a forest and there's no one to hear it, does it make a sound? Really, it doesn't, because in order for it to be considered sound, it has to go through this process where it is actually being perceived by either humans or animals or something. So this perception is very important, just as much as these physical properties of the sound are. And so I'm gonna go ahead and break down what a wave looks like, and we can go over some of the physical properties of a wave. So once again, I have my waveform, and we know that it's a waveform because of two things. So the x-axis is representing time, and this will usually be in seconds, and the y-axis is representing amplitude, and this will usually be in decibels. And basically, when we have our waveform, it will be, um, let's say that we have 2 seconds here. So it'll be like 1 second. And then let's see how many cycles I want to have. Maybe, I don't like how I drew that. Let me try this again. Sorry, clearly today's not my best artwork. All right. Let's see, one. You know what? Close enough. This is not a perfect wave, but just assume it looks perfect. So basically, there are different qualities that we can assess when we talk about a wave. So The first thing we could do is we can look at the cycle. So what is one cycle? Basically, a cycle is the repeated element. So there's this repeated um, pattern that kind of goes on with these simple wave patterns. And so you can tell because you see the starting point, and it's kind of a return to that starting point. And so here we go up into this area of compression, and then we go down to this area of rarefaction, and then we go back to equilibrium or original position. So this whole cycle, I mean, well, that's exactly the point I was making. This is one cycle. And based on this idea of a cycle, we can actually define two more words. So first, let me talk about frequency. So frequency is essentially how many cycles do we have in a unit of time? And usually it'll be like cycles per second would be the unit, which will be what we call hertz. So anytime you see hertz, you should immediately think frequency. And you should also understand what that frequency is representing. So in this case, if we're marking off 1 second here, then basically we can see, so here's one cycle, right? This is one cycle. And then we have our second cycle here. So we have two cycles in 1 second, and that's going to be 2 hertz. And some cases may not be as easy to spot. So for example, you should know, like, you can always just divide the number of cycles by the number of time to get the frequency. So even if I didn't have this 1 second mark here, if I see 1, 2, 3, 4 cycles, I see 4 cycles in 2 seconds, then I can just divide that out to get 2 hertz. Okay? And then now that we have this idea of frequency, we can also define what's called a period of the wave. And a period, the simple definition is it's 1 over the frequency. But what does that mean beyond this equation? What it actually means is how much time, how much time does it take to complete one cycle? So rather than seeing how many cycles fit into one unit of time, it's saying how many or how much time does it take to complete one cycle. And you can remember that easily because the word period itself refers to some amount of time. So it's just asking how much time has passed once this wave has completed one cycle. So in this case, we can see that in order to do one cycle. So this is one cycle here, right? And this is only half of a second. It's half of a second, so we can say like 0.5 seconds. But another way that we could have gotten that was to plug it into this equation and say, well, we know the frequency is 2 hertz, right? So we could say 1 over 2 hertz will give us our frequency of 0.5 seconds. So there are different ways you can measure this, but essentially, figure out whichever method you like best and just roll with that. And then the last but another very important characteristic of our waves is what is called amplitude. So amplitude, let me write that here. Amplitude is basically the strength of our wave, right? So let's call it the strength. And it's also known as the maximum displacement. Displacement of the wave from equilibrium. So going back to this example, so this line right here is going to be equilibrium, right? That's the resting point of the wave. And so the maximum displacement, remember from our basic physics terms, displacement is a change in position. So what's the maximum that this wave changes in position? Usually it's for this highest, this peak of compression, or it's the same as like this lowest point of rarefaction. But this displacement right here, this is what's known as your amplitude. And basically, the reason that all these terms are important to know is because when we perceive sound, um, some of these physical properties of the sound waves translate to how our perception of the sound changes. So this is where we get more into this idea of, so all this stuff before, this is the physical components of the wave. But now let's get into the perceptual components of the wave. And so, for example, we have frequency, which is the physical part, but frequency will actually translate to how we perceive pitch or tone. So, for example, if I have two waves, and this is equilibrium point. So one of the waves looks like this, and the other wave looks like this. Well, first of all, which of these waves has a higher frequency? Is it wave 1 or wave 2? So it should be wave 2. So this one has the higher frequency or higher number of hertz. And because of that, which one will have the higher pitch or higher tone or note perceptually? It will also be this wave, wave 2. Whereas this one, we can see the frequency is lower because there are less cycles per second. I probably should have specified that this is 1 second for both of these. And so because of that, we know that this wave, it has a lower frequency or lower number of hertz, and that's going to translate to a lower pitch when we're hearing it. And then in the same note, we can also talk about amplitude and how it's perceived. So amplitude over here, this is going to be related to the volume that we perceive. So how loud or how soft is something? And so let's go ahead and make another example here, where once again, I'm going to be comparing two waves. And this wave looks like this. And this wave looks like this. This is a really extreme example. But out of these waves, first of all, which one has the higher amplitude? It should be this one, right? Because there's greater displacement from that equilibrium point. And so this one has greater amplitude, so which one will be louder? It will also be this first wave. So the second, the amplitude is really tiny, and so the low amplitude also tells us that it's going to sound softer perceptually. And another thing to note is always know your units. So for frequency, it cycles per second, but really what we will be using is hertz. And for example, we will say like the human ear can hear 20 to 2 or 20,000 hertz, right? This is human range of hearing. Let me specify human range of hearing. And then for amplitude, on the other hand, we use something called the decibel. So remember, this is our prefix deci. So the decibel is what's used. We'll also write it out like this, like D with the capital B. And one thing to note is that usually our units are linear units where they're moving in very small increments, but this is actually a logarithmic unit. So it's moving in these larger increments. So logarithmic unit. So just something to note for that one. Um, let's see what else to talk about. How about I move on to the timing of waves? So the timing of waves boils down to what we call phase. So this is the timing of waves. Okay. And basically, there are two main types of, um, well, actually, let me just show you quickly what I mean when I say timing. So again, we have our waveform. And I'm gonna keep repeating this over and over that this is called a waveform. How do we know that? Because the x-axis is time and the y-axis is decibels or amplitude. And when we have this waveform, we have this kind of, we have our compression, we have our rarefaction, and basically, the time that each of these things occurs at is really important. So exactly how many seconds? Is this maybe 0.5 seconds that this is occurring? Is it 1 second? What is it? When is the compression occurring? When is the rarefaction occurring? This is really important because it tells us when we're experiencing these high pressure regions, when we're experiencing these low pressure regions because of the wave and how it's moving. And there are two ways of these waves interacting because, in reality, we don't just see a single sound wave propagating. We have multiple different waves and they're all interacting with each other in what we call interference. So when you think of interference, think of interactions. How are these waves interacting with one another? And we have two forms. We have constructive and we have destructive. Okay, constructive and destructive. So looking at this a little bit closer, let's just look at these words first. When we say constructive, what do we think of? Constructing means to build, right? So something is building up or maybe getting stronger, right? When we think of destructive, what do we think of? We think of the opposite, right? We think of something being destroyed, something being reduced. And these words give us a lot of insight into exactly what these types of interference do. So with constructive interference, basically, let's say we have these two waves, and at some point, these waves look like this. And what that means is that these waves are what we would call in phase. So in phase basically means that the timings are the same. So the timing, it all lines up, right? And basically when we go to add this, we see that these, if this is time on the x-axis, we see that the compression is occurring at the same time and the rarefaction is occurring at the same time. And what ends up happening is that the amplitude of the signal ends up becoming even more enhanced at that. Oops, I feel like I didn't draw this well. Becomes even more enhanced, okay? So basically it's almost like 2 times the strength of these two separate waves when we combine it to get this wave. And so yeah, so basically that is constructive interference. Now what is destructive interference? So let's say I have this wave that looks like this, and then at the same time, another wave is looking like this. Like this, okay? So as you can see, let's look at our areas of compression first. So compression is occurring in these areas, but they're not really lining up, right? Actually, they're kind of lining up with the opposite because the rarefaction here is aligning with the compression, and this rarefaction is aligning with this compression. So basically, what happens is that they cancel out, and the resulting wave is going to be negated. There's one compression, there's one rarefaction. So if you kind of take the average of that, you're just going to get zero, like the wave is at rest. So these waves cancel out. And so that is what we call destructive interference, is when these waves are, I would say, out of phase rather than in phase. So the timing is not aligning. And interference, it plays a lot of different roles in how we perceive sound. Basically, most sounds, it's not, again, you don't just see this like single sound wave in nature. That would be nice if we did scientifically, but really what we see is a combination of all these different waves with different frequencies, and the sum of all these little waves together is going to be what we perceive as the final sound. Okay. So now let's talk about how waves travel. So how do waves, oops, how do waves travel? So I'm gonna go over the first two pretty quickly because I feel like they're more intuitive. So we have absorption and we have reflection. So with absorption, let's say I have this wall here, and I have some sound that's propagating, and the sound hits the wall, but the wall is made of what I would call a dampening or damping material. And so what happens is the sound goes towards the wall, and then it just kind of gets absorbed by the wall. So this is essentially absorption. So when sound is propagating, some of it ends up getting absorbed into the the next medium or next object that it runs into. And this is the example of the movie theater that Dr. Wong was mentioning, or any sort of soundproof room. Basically, what's happening is you're putting this material that is specifically made to absorb the sound. And then as opposed to that, we have reflection. So let's say we have a wall again, probably a wall made of a different material, and the sound is coming towards that wall. And then when the sound hits that wall, it does a reflection, just like how light reflects off a mirror. Sound also can reflect off of this object or obstacle or something, and so it's reflecting, it's bouncing back, so bouncing off the off whatever that object is. Now, where it gets a little more confusing is when we get to refraction and diffraction. So let's start with refraction. So with refraction, one of the things to note is that it's a change in direction. But why is really the main thing we need to know. Why is it changing direction? So there are two reasons why. One would be a change in temperature. So, for example, if you go from warm air to cold air, that could cause a change in direction. And the other would be change in the medium, or the state of matter that it's passing through. So, for example, if I have this body of water here, let's say this is water, and let's say this is air, this will be our air. And, water is a liquid, air is a gas, they're different states of matter, which means that the speed and the characteristics of the wave, such as the direction, will change when it runs into a different state of matter. So in this case, if I have my sound wave and it's coming from here, and it's happy, it's just traveling through the air, and then when it hits water, it's actually going to change directions. Now I don't know how much it's changing directions, but let's just make it kind of dramatic for the example of like, demonstrating this concept. So it's like if the sound is moving in this direction and then it hits this other medium, so it changes direction. So it's a change in direction, but specifically due to either a change in temperature or a change in medium. So then by contrast, we have diffraction. So what is diffraction? Well, once again, diffraction is a change in direction. But the reason for this change in direction is a little bit different. So with diffraction, it's not because of a change in temperature or change in the medium. It's actually because of obstacles. So either one, it's passing through something narrow, so passing through a narrow opening, or two, it is passing around some obstacle. I don't know what obstacle, but it's passing around something, right? So, for example, if I'm standing over here and my friend, my buddy is standing over here, and then I have this giant rock, let me like label it, this giant rock in between, and I'm speaking to my friend. What happens is that this sound will honestly end up changing direction. And so some of that sound, it may not be quite as dramatic as this, but basically the point is that the sound starts off in one direction and then it kind of changes in another direction and moves around the obstacle, which is why even if I had this rock that was between me and my friend would probably still be able to hear me to some degree. It may not be a great quality of sound, but some of that sound is still traveling around the obstacle. And same thing, like if you have a really narrow opening or something, like we're back to our wall and there's this tiny little opening. And then let's say the sound is coming from this direction, then part of the sound is going to go through that opening. So there is this change of direction as well. So these two methods would be diffraction as opposed to a change in temperature or change in medium. And those changes in direction will be refraction. So make sure you know the difference between those two. And then, still on this note of how sound travels, we have two other concepts to note. So we have what's called an echo and what's called a reverberation. And the difference between this is important to know. So with an echo, the main thing you should be thinking of is it's a delay in sound. And it's usually caused by a single reflection. Maybe it may be like one or two reflections. It's not always just one, but it's kind of a more simple example of a reflection. So, for example, if I'm standing in this cave, and basically when I first speak, the sound is propagating in this direction, right? Actually, let me make this a different direction. Let's say the sound is propagating in this direction, and then it bounces off this wall and it comes back towards me. So the thing is, the first time that I hear the sound, it's actually going to be right when I spoke it. So my eardrum vibrates when I speak the sentence or say some sound. So the first time I hear it, it's going to be here. But when this sound bounces back, this is going to be my second time hearing it, but with a delay. So this delayed sound, this is called the echo. Okay? So it's a delay in sound. It's usually not this like overlapping reflection. Um, so the main thing to note is it's this delayed processing in the sound where you hear a second duplicate of the sound you originally already heard. And then by comparison, what is reverberations? Think of if you guys are into digital music or you sing, you can think of reverb with like a microphone. Um, but basically, a reverb or reverberation is not a delay in sound. It's more like this sustained, prolonging, dense sound. So let's say prolonged, dense sound. And it also has this really gradual decay. So what causes it? It's actually many, many, many overlapping reflections. And these reflections will basically cause the sound to interfere with one another. So there's this aspect of the interference we talked about before. It can be some constructive interference, some destructive interference, and it's all kind of summing together. So here, let's say we have our cave example. And so let's say the person speaks, the sound wave goes up here, but then it kind of bounces here, and then it goes here, and then it goes here, and here again, and you know, it's kind of going all over the place, right? Like it's going here and here, and it's having these numerous reflections, and what ends up happening is that you have this dense sound that slowly decays. So it feels like this really full sound that's lasting for a long time, and then it slowly decays. So that is what we call a reverberation. So make sure you know the difference with that. And then we'll talk about 3 ways to draw a wave. So to draw a wave. So this is kind of shifting gears a little bit. So we talked about the waveform first. And basically, the waveform looks kind of like this. We have amplitude in decibels, and we have time in seconds. And that's honestly the main thing that you need to know. The x-axis will show you time, the y-axis will show you amplitude, and then you can just draw your wave with areas of compression and rarefaction, all that good stuff. And then we have something else, which is called a spectrum. And a spectrum is a little different. So what a spectrum does is on the x-axis, we're going to put frequency instead, and frequency is going to be in hertz, right? And then on the y-axis, we'll still have amplitude, which will be in decibels. So make sure you know what items are on each of these axes. So basically, an example of this would be like sounds are complex, right? So many different frequencies may be there. So we can have all these different frequencies represented in the x-axis. And then there are different amplitudes for each frequency wave. So let's say we really hear that 10 hertz wave. So that one it has a higher amplitude, right? That must mean it's louder. And then let's say we don't hear the 20 hertz as much, and then 30 is in between. So this is kind of what a spectrum will look like. And then rather than memorizing like what the signal looks like, I would say memorize these axes. So x-axis in this case is frequency, and the y-axis is amplitude. And then we have a spectrogram. So for the spectrogram, what we end up having is the x-axis once again is going to be time in seconds. Then the y-axis is going to be frequency this time. So it's not the same as a spectrum. In a spectrum, the frequency is the x-axis. In a spectrogram, the frequency is the y-axis. So this will be in hertz. And let me just, okay. And so basically what this will look like is we want to see, okay, if someone's talking, for example, 1 second after they start, what all frequencies are represented in their speech. So we may see um, some 10 hertz sounds, and then we may see some 20 hertz sounds. And so basically what you'll end up seeing is this order where we break down exactly what frequencies of sound are contained for that given time interval. So now we're gonna switch gears again. We're covering a lot of content because this is me redoing both parts 2 and 3. But we're gonna move on to simple harmonic motion, which I do realize that some people were kind of confused about this concept and how it's relevant to sound. So I'm gonna try to clarify this. You can also call this SHM as like a little shorthand. So simple harmonic motion, basically, let's say we have this pendulum or like a swing and we have a ball attached at the end and we bring it up from equilibrium, this certain amount. And basically when we let it go, what the pendulum will do is it'll swing all the way to kind of this opposite position. And then, so this is basically the initial displacement. And what will happen though is that there will be something called a restoring force that brings the pendulum all the way back to its original position. So it brings the ball back to the original position. And so simple harmonic motion, this idea is following this whole pendulum principle where basically the amount of displacement or the displacing force is going to be equal to the restoring force. So what does that mean in a waveform? Basically, you don't need to know a bunch of the details behind this, but if this is your waveform, and again, we know it's a waveform because time is on the x-axis and the y-axis is amplitude, and basically we're going to see this really simple wave that looks kind of like this. And this amplitude for the compression will be the same as the amplitude for the rarefaction. So let's say amplitude for the compression is equal to the amplitude of the rarefaction. And so you don't need to know a whole lot about the nature of simple harmonic motion and sound, but you do need to know about how is this perceived. So how is simple harmonic motion perceived? So to a listener, this will be a pure tone, which basically means there's only one frequency, there's only one amplitude. So we'll call this like a single frequency or single hertz sound. And in nature, though, the thing is we really don't see this. So this is not found in nature. So we'd have to kind of artificially manufacture one of these sounds. So if pure tones or these simple tones are not found in nature, then what is found in nature? So that's when we get to, as opposed to pure tones, we end up with complex tones. So yes, we have complex tones. And basically within complex tones, so these are the tones we do find in nature. This can be speech, it can be music, really anything. Even a tuning fork is not fully a pure tone, although it's close. It's not fully a pure tone. So really any sound we encounter in nature is going to be a complex tone. And within complex tones, there are actually two different types. So there is periodic, and there is aperiodic. So once again, before we actually like dive into what each of these terms mean, let's just look at the name of these. So we have periodic, and that word itself is going to mean something is repeating, something is predictive or predictable, I should say. And then this one, aperiodic, is just the opposite, so it's not repeating. So basically, complex tones that are periodic, they're still complex, right? So they're complex, but they have some repeating nature. And they're basically a combo of a bunch of pure tones. And this is where interference and everything comes in, because all these pure tones have their own sound waves and they're interfering with one another. And so they sum up or combine to become this complex tone. So if we had this kind of waveform, once again, with seconds, decibels, basically we'll see something like this sort of thing. So there is this repeating pattern, right? This still makes one cycle, and we can clearly define this cycle. So this is something that's repetitive. And what we hear is basically it'll sound like a single note. So it sounds like one note or one pitch, but it's not a pure tone. So what is the note that we hear? This is called the fundamental frequency, or F naught. So fundamental frequency, and you should know this. And this is something we'll also talk about more when we do our prop tutorial later on in this course. So this is called F naught, or the fundamental frequency. And so basically, if I were to make a spectrogram instead, so spectrogram, remember, is time on the x-axis, and then we have frequency or hertz on the y-axis. So basically, let's say that our fundamental frequency is 10 hertz. So we're going to see our fundamental frequency right there. But there's also something called harmonics. So then we have these harmonics that are multiples of F naught, or the fundamental frequency. So multiples of F naught. So even though we hear one single tone and it may sound like a pure tone to us, in actuality, it's F naught plus these harmonics. So plus these harmonics. And so, for example, like if my F naught, or fundamental frequency, is 10 hertz, then I also will have harmonics at 20 hertz, 30 hertz. It's going to be multiples of 10. So 10 times 2, 10 times 3, and I'll also see these little harmonics there. But the fundamental frequency that we perceive will be at 10 hertz. So yeah, I would say the other thing to note is what sounds will be periodic sounds. Usually it's going to be voiced sounds, mainly vowels. And you also hear this with singing. So when I sing a note and I'm singing in tune, you hear a single note because it's a periodic sound. And so you will hear the fundamental frequency, but it's not a pure tone. But then we have aperiodic, and aperiodic is looking a little crazier than periodic. So if I have my waveform again, so remember we label our axes, so it does not have a repetitive nature to it. So it's just gonna kind of look like some sort of craziness, right? And in reality, when we record speech samples and research and everything, this is what it kind of looks like. So the signal looks very noisy, it looks very random, and usually we'll see it in things like whispering, or voiceless sounds, which is important to note since voiceless mostly. But it can also be random stuff like applause or other random sounds. And within aperiodic, the important thing to note is that there is actually another subdivision. So remember, complex tones can either be periodic or aperiodic, but aperiodic sounds can also be divided into two categories. There's transient and there's continuous. If I can fit that in. Maybe I'll just rewrite that. Okay, so transient and continuous. Now, once again, before we actually dive in and analyze what these concepts are, let's just look at the word. So what does the word transient mean? So transient means that something is fast or it's fleeting. It's there 1 second and gone the next second, that kind of thing. So that's what the word transient means. But continuous, on the other hand, you know what it means. It means something is long lasting. It means that it's prolonged. And the reason that I am making you guys kind of break down these words before we go into it is so that it actually helps you remember it better. So if you remember the definition of transient, then that will help you remember what the concept is. So when we think of transient sounds, the best example will be what we call voiceless stops or plosives. And when we learn more about phonetics and the articulators, you'll learn more about what these concepts are. But my examples and Dr. Wong's examples would be t, k. So remember, they're voiceless because aperiodic sounds tend to be this kind of voiceless quality. There's not voicing, right? And these stops or plosives, they're very fast sounds, right? They're very fleeting. So p, t, k. None of those sounds last very long. So they are transient aperiodic sounds. They're voiceless sounds. They're very fast. They don't repeat. I'm just trying to find some way to like summarize with aperiodic. But yeah, I hope you get the gist of that. Now, by contrast, with continuous sound, so for one, they are still voiceless because they're aperiodic, right? So that goes with the territory of aperiodic. But this will be more like fricatives, which again, you will learn more about these definitions when we dive into that part, but it'll be sounds like s, sh, or even though the sound's shorter, it's actually considered a fricative sound. And if you haven't learned IPA, I'm just gonna jot down these little pronunciations. So fricative sounds, they last a long time. It is this continuous airflow that's going on to produce or s, as opposed to p, t, k, which are very short sounds. So just note these differences. You should know the difference. So what is a pure tone versus a complex tone? What is periodic versus aperiodic? And what is transient versus continuous? And the next thing that I wanted to talk about is kind of switching gears, but it's about natural frequency. So basically, natural frequency is this idea that all objects, or matter have a natural frequency, or NF, as you could also call it. And basically, this natural frequency, um, it's determined by physical characteristics. So let me say determined by physical characteristics. So this could be shape or size, material it's made out of, um, the density. It can be a lot of different characteristics, but it's determined by these characteristics of the object itself, of the object. And basically, the example that I like using is let's say you have this glass. So this is glass, okay? And the example that I often use is of an opera singer. So I have this opera singer who's singing all these pretty notes, right? And you may have seen in cartoons that basically the opera singer shatters glass. So you'll kind of see these sound vibrations are propagating and the glass starts to shake and it shakes and then finally it it shatters or it starts cracking. So why does this happen? It's because the singer matches the natural frequency of the glass. And so this is actually possible where the singer can match the NF and therefore cause this kind of physical reaction within the glass. And this process where the NF is matched, the natural frequency of an object is matched, this is called acoustic resonance. So it's matching the natural frequency. And acoustic resonance becomes important because it's kind of the basis of different types of filtering because it allows you to amplify some sounds and dampen others. So I'll say basis of filtering. Um, and then speaking on this note of filtering, I'm just gonna briefly go over the different types of signals, or sorry, filters. I'm getting tired now. So there's low pass, there's high pass, band pass, and band stop. So when you hear this term pass to begin with, think these are the frequencies that are allowed by the filter. And when you hear the word stop, vice versa, think these are the frequencies stopped or omitted by the filter. So when we say low pass, for example, so let me create this little, so in this case, I'm gonna make my x-axis frequency in hertz. So x is gonna be frequency, which is in hertz. So with low pass, for instance, this means the lower frequencies are allowed by the filter. So basically, first I have to create what's called a cutoff frequency. And the cutoff frequency can be anything. So let me just set this for fun as 50 hertz. So in a low pass filter, it says only frequencies below the cutoff are allowed. So this is below the cutoff, right? So this is less than 50 hertz. That means that it's allowed. But anything above that cutoff is not allowed. So anything above 50 hertz will not be allowed. And 50 hertz is just a random number I came up with. You can choose whatever cutoff you would like. Usually it depends on the type of research you're doing and what you want to filter. On the other hand, high pass filtering, so let's say I had the exact same cutoff, just for fun, of 50 hertz. But high pass says that the higher frequencies are passed or allowed by the filter. So that means that only the frequencies above 50 hertz, greater than 50 hertz, these are allowed. But anything below 50 hertz, anything below the cutoff is not allowed. And then band pass basically is kind of like if you combine the two, like if you add a low pass filter and a high pass filter, and this area in between, this is called the band. So the band just means between two different frequencies. So for example, if I set this as 20 hertz to 50 hertz, also again, all random numbers that I'm just pulling out of my head at this point. And so basically what the bandpass filter does is within this band, we will allow all the frequencies. So if it's between 20 to 50 hertz, it's going to be allowed. But anything outside of the band, anything outside of that range, we will not allow. And band stop is the opposite of that. So once again, we can have this band of 20 hertz to 50 hertz. But what band stop says is, I don't want those frequencies, but I want everything else but those frequencies. So this is where we'll allow if it's greater than 50, oops, greater than 50 hertz, we allow, or if it's less than 20 hertz, we allow. So these two sides are allowed, but anything within the band is not allowed. That is like a bulk of the concepts. The other thing I would just note, also kind of a random topic, would be the shape of resonators. So the shape of resonators. Basically, like Dr. Wong was talking about birds, like songbirds and other animals, they'll have very simple resonators. Simple resonators. And the shape and everything is not very complex. And so even though they are capable of a variety of sounds, um, as opposed to humans, it's a pretty simple anatomy. So then we have humans. Oh, I don't know how to draw a human, but just pretend that that's a human. Oh no, this looks so bad. I don't know what I'm gonna do. I'm trying to draw like a side profile. Just pretend that's a human. Humans actually have really complex resonators, and we're going to talk about the details more. You really don't need to know the shape or anything. They're complex and kind of irregularly shaped resonators. And as a result of that, this allows for more complex sound production, which is actually a really cool aspect of speech science, is understanding why humans have this unique ability for complex speech. And part of that lies in our resonators that allow us to produce so many different types of sounds. So that is about it. I think that's a pretty thorough, between this and video one, you should have most of the main knowledge for the exam. Is it everything? I don't know. Like, I would say it's mostly the major stuff, maybe like 70-80%. So go ahead and review these. Ask me if you have any questions before the exam. Yeah, that's about it. I hope this was helpful for you.